So we will start by describing the most generic BRAM HDL template, and that's for a synchronous dual port RAM. And to show you some sort of a block diagram for it, what we have is we will force Vivado to interpret this to utilize the BRAM to implement two-port synchronous dual port. It's dual port, but each one of these ports can be write or read, but not simultaneously. Okay, so let's get started with that by going to Vivado. So we're going to go to Vivado, and I have started something in here, and it's basically synchronous dual RAM. Let me just do this here. Okay, so you can see it. So what I have started with, as usual, with the input and output already specified, and I already used the parameters. This time the parameters, I made them a little bit different just to show you. So I specified that the address width should be 10. That means I have 1024 rows, or like 1 kilo basically, and that's each one of them is 8 bits, so it's 1 kilobyte memory if I actually interpret it with the default parameters. Again, what you like you see in the graph, I have a couple of ports. Both of them can be read or write, so I'm going to have write enabled for A and write enabled for B. Let's call them port A and port B. Port A can have actually an address, and port B should have an address too. And that address, whenever you specify, you can either write the in into it, or you can read the out of it. So let's see this. And generally speaking, it's synchronous. Everything is synchronous. Whenever you're using BRAM is wrapped in circuitry that makes it synchronous. So generally speaking, you're not going to get asynchronous read or write. So let's do that. The way we're going to start is by specifying exactly what we did for a generic RAM. What you need to do is you need to specify at some sort of a memory. You can call it memory, RAM, whatever you want to call it. And I specified it as address width -1 in here. This is basically exactly the same as before, nothing different. So now what we're going to be doing is I'm going to deal with two ports. So first is port A. I'll do always FF, and because it's synchronous, and I'll do, let's make it operational at the positive edge of the clock. And now we have begin and we have end in here. So inside, what we're going to be doing is I will ask if, because I'm in port A, is write enabled. Basically, I'm prioritizing the write over the read. So I'm asking, is the write enable for port A? If it is the case, I will actually write to the memory as specified to port A, or to address A basically, the D input A. That's basically what I'm doing. So you can see in here, I'm asking if the write is enabled, I'm writing to the memory in row that is specified by address A, whatever I put on the input for A. Okay, and now if I want to read, that means the write enable is not enabled in here. What we're going to be doing is we're going to say, well, the data for A is going to be memory address A. And that's pretty much for port A. This is how port A operates. And again, as you specify in here, if I issued a read and write at the same time, actually I can do read and write at the same time, but if I'm doing it, you're going to see that I'm prioritizing the write first. Okay, this is not happy in here for some reason. Let's see, because I called it data A, but it's not data A, just to specify that this is basically the out of A. So how do I write for port B? Well, you just copy and paste it. It's the same exact thing. Okay, so we have in here, this is port B, and I'm asking for write enable B for the address of B, and this is for B in here. So all I have to do is just change it to B, and now I have it. So if we take a look at what the RTL analysis would be by looking at the schematics, we're going to see it interpreted as an RTL RAM, and it registered the D out for A and the D out for B because I want it to be synchronous and so forth. So let's see the utilization. This is kind of old, so in order for us to know what type of utilization, whether it actually used BRAM or whatnot, we're going to have to run the implementation one more time and wait for it to finish. So now that it has finished, we can take a look here at the bottom, and you can see that it did not use any lookup tables or flip-flops now. It only used about half of a BRAM because it didn't need all of it. Remember, a BRAM can be split instead of 32 kilobits into 18 kilobits, and if you calculate it what we have written, you're going to see that this here by default it's going to be only 1 kilobyte, or you can think about it as 8 kilobits. Okay, so it's less than the 18, so it only used half of a VRAM. It didn't need any lookup tables on flip-flops. Okay, so what happened in here? So just to summarize, what happened is we have written certain code that Vivado interpreted that you need to use as a VRAM. Where did I get this code from? I got it from this particular link in here. So if we take a look at that particular link and we get to see what would happen, and you can see that this is basically a Vivado synthesis guide, and within chapter 4, under, I believe it's RAM HDL coding technique, you can see that there are coding techniques in here between distributed RAM, dedicated block RAM, and whatnot, and it actually just tell you the differences and single port or up to 2 write ports and whatnot. So if you go through it, you're gonna see a bunch of tables in here. I think it should be at page 122 or so, something like that. You're going to see that a bunch of templates. So if you follow these templates, it will actually interpret it to be BRAM. Okay, so here's a single block BRAM. If you do this here, if you follow the exact template, you're going to do that. So in order, if you do any little changes, Vivado might not interpret it as BRAM and might revert to going to lookup tables and flip-flops. So if you need any deviation from the codes or the templates I'm showing you, my recommendation is put them in a separate file. So in here, let me just do that here one more time. So put this in separate file in here, for example, and instantiate an instant of that in a different file and wrap it around with different files or different inputs and outputs and circuitry as you see fit. So let's build another BRAM RAM, and now we're going to do the simple synchronous dual port RAM. And what you're going to see is, as opposed to the dual RAM that we've seen, here I have 2 ports. One is dedicated read and the other one is dedicated write. As in comparison with the synchronous dual RAM you've seen before, the other one had 2 ports. Each one of them can be read or write. Now we're going to have a dedicated read and a dedicated write. That's the difference. So let's go to Vivado and see what we need to do. So in Vivado, I basically put the inputs and outputs, and you can see the address width and the data width in here. We have a clock and a write enable. I only need one single write enable, so I just need that. I need an address for the read and an address for the write, because one of the ports is read, the other one is write, and I need one data for input for the write associated with the write and one for the output associated with the read. And what I have done is I copied the code from the synchronous dual. Just as a reminder, we do have a port A and it was a read and a write, and we had a port B and it's a read and a write. I don't need 2 anymore. What I need is I need to say, well, if write is enable, what we need to do is the address for the W, which is write, we're going to just basically take the DN into it. And for the write, because this is for the write, for the read, all we need to do is basically the D out. We should read it from the memory in address specified by read. And that's as simple as it is. There's nothing else to it. Okay, so what we're doing is in here, this is the same memory place. I have a port that will be dedicated for the write. I can specify the write address and the D out, and the read address I specified and the DN, and both of them are synchronous. And just to make sure, we're going to actually go run the implementation and see that it actually uses the BRAM. It doesn't interpret it as a lookup table or whatnot. And as we expected, it only used the BRAM. It did not use the lookup tables. And again, this happened because I followed the description coming from the Vivado synthesis guide, because I followed a very specific template. If you deviate a little bit from this template, Vivado might or might not know that you want to use BRAM. So the last example for BRAM HD templates is the synchronous single port RAM. Okay, and in this particular one, I have one port, and that port can be either read or can be basically used for read or write. So you can't do read and write simultaneously. So let's go to Vivado and just do that. So you're going to see that I have started it already. I have the input clock, the write enable, and I only have one address this time. I don't need an address for read and an address for write because I only have one address. So I'm able to do a D in or a D out, basically a read or write. And I have kept it for A, D address A, D in A, D out A, because I'm going to go to the first one we implemented, and I'm going to show you that we really are implementing the same exact thing, but instead of having a port A and a port B, all you need to do is just basically specify that you have port A alone, and that's it. So again, if you take a look at this code in here, you do have one address. So within this one address, I believe it didn't like the write enable A in here. Okay, so within this one address, you can either write into A or read from it, but you cannot do this simultaneously. Yeah, and it's not liking something in here, and that something is because I didn't specify the memory, so I have to also copy the code for the memory itself. So I'm going to copy that code in here and put it right there. So this next template in here, you're going to see if you implement it using the run implementation, you're going to see that it will actually use the BRAM. So let's do that. And as we expected, it only used the BRAM, no lookup tables, no flip-flops, just the BRAM. So to recap, what we have seen is we have 3 BRAM templates. So the synchronous dual port RAM in here, and we have seen the simple and the synchronous single port. The synchronous dual port RAM, the one we stopped at here, is actually the most generic. What it has 2 ports, the red one and the blue one in here. So the red one can be used as read or write. You can't do both at the same time, but you can either read or write because you only have one address in here. Okay, and the same goes for the blue one. You have either a read or write. You can't do both at the same time. And then what we did is we moved on and we saw a simple synchronous dual port RAM. And the reason why it's called simple, because I have dual port like the one before it, but each port is dedicated for one of the operations. One is dedicated for read, the other one is dedicated for write. Okay, and the last one we have seen is the single port RAM. It's all of them are synchronous, as you can see. Okay, and it's dedicated here. It's very similar to the dual one, but what I have is I have a single port that can be used as read or write, but they cannot be used simultaneously, so you can't read and write at the same time. And those are the differences. If you follow these templates, you will force Vivado to actually implement this in BRAM.